Shall I?
Yes, the session has been started, live streaming on YouTube. We can proceed with the session.
A very good afternoon to everyone. The future is green energy, sustainable, and renewable energy. Energy conservation is the foundation of energy independence, said by Tom Allen. With this quote, I welcome you all on behalf of Department of Electronics and Communication Engineering, Savita Engineering College, who has brought all of us together for the webinar on partial shading of PV panels, MATLAB Performance Analysis. Let me introduce my college. Savita Engineering College, Department of ECE, has established in the year 2001. Our vision is to develop art with center of excellence in electronics and communication engineering education on par with global standards. The Department of ECE as well experienced faculty of proven ability and diverse specialization. The faculty actively involves themselves in research in the field of robotics, VLSI, MEMS, image processing, and embedded systems. Savita Engineering College, established in the year 2001, an autonomous institution which follows the Finland based education model, and we march towards less is more concept. Our college makes the students job ready by providing Industry 4.0 ready curriculum which imparts the 21st century skills. Project based learning integrated with subject improves the student's skill set and makes our learners to be the best, which is the motto of our college. Now I invite Mr. M. Praveen, Assistant Professor, ECE Department, to introduce our chief guest. Please, sir.
Thank you, ma'am.
M. Praveen, sir.
Let me introduce the chief guest, Dr.Ezideen Hasso, as a professor of Mechatronics Engineering at International University, Erbil, North Europe. He has obtained his doctoral degree from University of Manchester, UK. In Electrical Engineering Department, Sir has carried out various research activities, which includes electric vehicles, VFD power electronics for induction motor driver, VFD power electronics for BLDC motor driver.
Okay, let me introduce the chief guest. Dr. Ezideen Hasso works as Head of Department Mechatronics Engineering, Tishk International University, Erbil, North Iraq. He has obtained his doctoral degree from University of Manchester, United Kingdom, in Electrical Engineering Department. Sir has carried out various research activities which includes electric vehicle, VFD power electronic for induction motor driver, VFD power electronic for BLDC motor driver, biofuel from used cooking oil, biodigester for domestic and commercial scale size, test station for integrated circuits, electrostatic blanking system for the electron beam machine, design and implementation of sun tracker for solar panels, water to fuel for transportation, encryptor for RF communication, hydrogen for military applications, and many more. Sir has started his career as engineer and demonstrator at the Control Engineering and Signal Processing Laboratories, University of Baghdad, Iraq. He has also been director of Cool Mobile SAR, Morocco, company director of Evergreen Energy Limited, and also he has been director of Phoenix Sky Limited. Welcome you, sir. The session is yours. Sir, please unmute yourself. Thank you, sir.
Okay. First of all, I'd like to thank you very much. Ms. Priya, yeah. I would like to thank you very much for the great introduction. And I would like to thank Ms. Elizabeth and Professor Praveen as well. To start with, it is a really great honor to be among you guys. And I would say, good afternoon to you all. And for the people who are in this part of the world, I say good morning to them. And I hope you are all, during this hard time, the pandemic, I hope you are all safe and well. Let me, I need to share my screen first to start my, the noise. Yeah, if can. Yeah.
Yes, sir, you can share your screen.
Yeah, see now. Yeah, can you all see?
Uh,
Yeah,
it
I've
should,
already shared the
yes,
screen.
sir.
Yeah.
Yes, sir.
So can you all see me now? Okay. Yeah.
Yes, sir. Yes.
Okay then. Today's topic is about partial shading of PV panels, photovoltaic panels. We know photovoltaic, they are how they work. But I would like to concentrate today on partial shading. What if we have a partial shading panel? What will happen? Okay, or say one of the cells in the panel is shaded completely or partially. What will happen? The host really, they've done a great job, introducing me. So I don't think I need to say much. This is my name, Ezideen Hasso, and I'm head of department at Tishk International University in Erbil, which is the capital of Kurdistan in Iraq. The electricity actually is very important for us in our lives. So we cannot. I personally, I cannot imagine, life without electricity. But mainly, the electricity is being, from fossil fuel or from a nuclear. There are, of course, the renewable energy, and which is, today's topic is under, under this umbrella, the renewable energy. And some people may think, the electricity is only recent, only in the recent history. But actually, it was found, that even more than 2,000 years ago, people were using electricity. And I came across this actually. There is something called Baghdad battery, and this was discovered near Baghdad, I don't know, around 20 or 30 miles from Baghdad. It was excavated, from underground. And it's like a vase. And it was, they found it, they thought is something for decoration. People at that time, they were, I think it belongs to 200 or 300 BC. And they thought this was a vase for decoration. And then it was in the museum somewhere in Baghdad, I think, until somebody, a German guy, he came and he found it strange, So he investigated and he found it is actually a battery, is acid battery. I built this with my students. We built this, So if you have two poles, say one copper, one iron, and just dip them dip them in some sort of acid. We used vinegar. So if you do that, we got actually 0.5 volt from this battery. So some people may wonder, what the people at that time they were using this battery for. I personally think, it was for gold plating. So if somebody's wife, putting pressure on him to buy her gold, so he will cheat. He will go and buy silver and get it coated with gold and bring her the the gift as a gold, whereas it's actually inside is only silver. Yeah. So you ladies, girls, in the audience, don't get cheated upon by this trick. Okay. Um, okay, so solar energy source, is quite viable because it's already in use in many countries, and this could be, like grid tied or as standalone systems, and the efficiency usually of these solar panels is between, I don't know, 12, I would say 12, 13% up to 20, 22%. Although they are now new in the market, some systems that can go up to 40, on some claims, up to 45 as well, but still really is quite low. Okay. This is a real problem, for solar systems. Not only that, because the solar system is only for limited hours, so it's not available all the time, 24 hours. Unlike, say, the wind, even the wind is not always, but at least it doesn't matter whether it's day or night. Still, the wind will blow. Today we'll be looking into these items, the PV cell electrical equivalent circuit, and in order to analyze it, and we'll be looking into the diode, because the PV cell are simply diodes. If you cover it, if we cover the photovoltaic cell, it becomes a diode, but the only thing is a big surface area. So we'll be looking into that. And then I will talk about the partial shading and the cause and effect of partial shading in panels. We'll do circuit analysis of the panel. We take a panel, and we analyze the circuit of this. And then I'll be doing some modeling on the MATLAB. Although I've done them, so I only got you the screenshots of this modeling. Okay, the solar constant is not unlimited, it's only limited. So it's about 1.3 kilowatt per square meter. And there is another term we usually use is the sun hour. So the sun hour is about 4 to 6 hours. This is the average around the world. This is, if we convert this figure 1.3 kilowatt to equivalent current at household, we have 250. I think in India you have 250 as well, I believe. So if we take that, it will be actually equivalent to 6 ampere per meter. Is quite a lot. But of course, we said the efficiency of the solar panels are quite low. So around, between 13, 15, 16, in most cases, but there are some up to 20, 22 as well. So the efficiency is quite low. The photovoltaic are simply, if we look at it, as a system, as a box is really simply electron converter. So it's photon to electron. It takes the photons and convert them to electron, free electron that they can move around these circuits. Okay, so is a simple definition of a photovoltaic cell is photon to electron converter. And of course, each one, because it's a diode, each one, and the diode is forward in the forward bias, it gives us, around 0.6 or 0.7 volt across it, between the anode and the cathode. Yeah, there are some terms, like the solar constant is simply the radiation, the solar radiation that reaches us. And this can vary due to different factors, such as clouds, or if it's beginning of the day, near the sunrise, or near the sunset afternoon. Of course, this will vary. The solar constant will vary. Usually, is the maximum we consider is around 1,000 watt per square meter, because the rest, although theoretically we have 1.3 or more than 1.3 kilowatt per square meter, but the usable ones and the one that reaches us actually is only 1,000, or the one that we can harness. There are some terms, I don't know if I'm going to mention them, like MPPT, maximum power point tracking. We need that because you are electronic engineers, I believe, most of you. And in order to convey, maximum power, you have to match the load. In communication, if you don't do that, you will have reflection, okay? In transmission lines, if you don't match the load with the transmission line, you will have reflection. So here the same thing, in order to get maximum power from the solar panel, you have to match the internal resistance of the panel with the load, with the equivalent resistance of the load. And this is done by some techniques, and usually we call them MPPT, maximum power point tracking. It's simply, if we look at the photovoltaic cell, we could represent it by a diode of 0.6 or 2.7 volt. And the equivalent circuit, this is the equivalent circuit for a PV cell. So it contains a current source here. This is a current source, and then an ideal diode with couple of resistances. There is a series resistance, which is in the order of, I don't know, 20 to 30 ohm in this order, or could be less. Okay, and here about 300 ohm. Okay, for today's purpose of the analysis, I'll just assume, we have an idealistic panel. These are parasitic resistance, we'll ignore them. So I'll assume this is too big, for the circuit, so I can ignore it. And this one here, this series one, is too short, and I can ignore it as well. These are the terms, as we said, it receives the solar constant here, the radiation, and converts it into current that flows in the circuit. Okay, so as I said, I'm going to simplify this circuit. If I take out these parasitic resistances, I'll be left with the current source and the ideal diode. We all know the diode, the characteristic curve for the diode, I think. You're all aware of that. Now, before I mention this, if I said earlier, if I take this and cover it completely, a cell, and I cover the cell completely, I don't allow any light reaching it, the cell becomes a simple diode. Although it's quite big, big size, because of the surface area. But it is a simple diode. So it will be like this. It will be just a diode if I give 100% shading. Now, what I'm going to do here, I'll assume a panel. Okay, so we simplified this circuit. We said is we're taking out the resistances, so we'll be left with the current source and the diodes. And then what I'm going to do, I'll just assume, sorry, where's, okay. So I just, I don't see a full screen here of me. So anyway, yeah. So each cell I could replace it with a simple battery. Okay, a small battery of 0.6 volt or 0.7 volt. Okay, and then what I'm going to do, I'm going to cover one of them, one of the cells here, as you can see here with the black. I'm assuming this is 100% under shade. So there is no light reaching this one. So when there is no light, we said it becomes simple diode. The cell actually produces current, sorry, in this fashion. So this is the positive side and this is the negative side. Okay, but now we have a diode here in this circuit. This is a big circuit. Say, I don't know. Usually we have 72 cells in the panel. They're all connected in series. This is most of the panels nowadays. They manufacture them this way. What we have here, we have a diode here, and for the batteries, if we assume the rest are still working as batteries, we'll have this diode is running in the reverse bias mode. Okay, so is blocking any current to go through the load. Yeah. If this is the case, now what will happen? Of course, the battery here will be gone out as well, so it won't be behaving like a battery. And now there are some points I want to refer to. We have here now. This is electrical circuit, and there are connections, but there is no current going through the load. So if we assume this is a 0 volt, this is a ground, this is a 0 volt, what will be the voltage drop across this load here? It will be 0 because there is no current, okay? Only the leakage current through this diode will be passing, and this is a small amount, usually micro amp, okay? So what will happen here? We have no current. There is electrical connection, but there is no current going through the load. If there is no current, whatever the voltage here, it will appear here, yeah, because the drop here is 0. So this will be at 0 volt. This is a 0 volt as well. This is ground. Then we have at this point A actually, we'll have, since this is a ground and this is a battery, we can add them together and replace them with a big battery. And if I have, say, if I have here, say, M cells in the upper part here, M cells, then this battery, I can replace it with M times 0.6 volt battery. But the upper side of this battery here, this is connected to the ground as 0 volts, so this will be negative M times 0.6. Now let's look at the lower half of the circuit here. What happens here? Let me assume here I have N cells, okay? then this side, because this is 0, this side here will be N times 0.6 volt. What will be VAB, the voltage difference between point A and B? It will be, summation of M plus N multiplied by 0.6 volt. I don't know if you are following me with this one or not, but if you just think about it, you will find it makes sense, okay? So the voltage VAB, it will be negative, okay, minus 0.6 M plus N number of cells, okay? So basically it will be number of cells, total number of cells, less this one here, the covered. We're assuming just a single cell is covered, okay? If it's 2, then it will be 2, okay? 3, and so on. But we're assuming just 1. So it will be the rest of the cells multiplied by 0.6 volt. And this will be in negative across this diode here, across this diode, okay? This is the characteristic curve for the diode. So the forward bias here, this side, and this is the reverse bias. The forward bias here, this is the knee here, this is about 0.6 or 0.7 volt, here. And this is for the silicon. For germanium is usually around 0.2 volts only, okay? But for solar cells, we usually use silicon to give us a higher voltage, which is 0.6. So this diode here will be in the reverse bias, as we said. If this voltage, if a panel, of 72 and is quite big, and this, say, this photovoltaic cells is not being designed to take this amount of reverse voltage, then it will be here beyond the the knee here, beyond this knee, and this is the breakdown. So it will be working beyond the breakdown, and it could damage the panel. It could really damage the panel. Okay, this is just the same diode, the characteristic curve of the diode. Okay. And because the power dissipation equals voltage times current. So volt times amp is the dissipated power on this device, whatever it is. In our case, is the diode, so it's the power dissipated on this diode. Okay, now I've finished the analysis of the circuit, in terms of electrical circuit or electronic circuit analysis of this panel. Now I'll be talking to you about something called Simscape in MATLAB. I'm sure you all, aware of the MATLAB, or some of you perhaps used it, or even the Simscape. I don't know if you're familiar with it or not. In MATLAB, what we have the command window, where this is the man-machine device, okay, or gadget. So we have the command window where we can, type and get answers from MATLAB. Okay, we have the script file, or some people call it the M file. So this one as well. We can write, instructions in terms of script, and we get answers. Okay, so it's like any other computer language, like C or Python or whatever. Okay, and then there is, for the simulation side, we have Simulink. I'm sure most of you, if you not used it, perhaps you've heard about it. The Simulink is block diagram level. Okay, like in control systems, what we have a block. There is an input to the block, and there is an output. The energy, it doesn't go backward. There's only one direction. Okay, the energy in the block diagram is only in one direction, runs in one direction. With the Simscape, is actually is a component level. You can simulate your circuit, your system to a circuit level, so component level. So I can have a resistance, I can have a diode, I can have capacitor, inductor, whatever, all these things. And then I can have a voltmeter, a meter, scope, oscilloscope. I can have all these things within the Simscape. Of course, the Simulink, they support partially some of these functionalities as well, but the Simscape is physical level, okay? Physical level, and the energy can move freely in either direction. Say in a two-port device like a resistor or diode or whatever, the energy can move, in this direction or in the opposite direction. Because it's a physical component, physical level simulation. So keeping this in mind, okay, let's look into something here. This is a circuit. Don't get overwhelmed with all these blocks, is actually, let me just see if I can do something. This is really simple. uh, Let me control P. What's happening? I cannot use the pen, or can I? Okay. So if I say whiteboard, so it's simple. I have a a battery. In this particular circuit, I have 3 batteries, which are 3 cells, and then I have a simple load here. But all the other blocks you've seen, I've inserted an ammeter here, and I've put a voltmeter here, okay? And then I have an oscilloscope as well. And what else? And then I control the amount of energy, the solar constant, to these photovoltaic cells individually. Okay, so don't get overwhelmed, with with these blocks. Too many blocks is basically is very simple. I have just the panel or few cells on the left, and then I have the load here. This is the RL. Okay, so just to let you know that. Okay, so if I say I think Control E, yeah. Okay, so these are the 3 cells here. Where's my pointer? Control, okay. So I have, this is one cell, this is the other cell, and this is the 3rd one. And here I have the load. This is the resistor, and this is the load. Okay. Here, this is the ammeter, which I told you about. This is the voltmeter. And here, these are the display. Okay, these are the display. Although I haven't used an oscilloscope here, but these are just like the screen of the ammeter. The Evo. So this is the screen of the Evo. This is the screen. And here, actually, on this one, in this particular one, I've used the product here to multiply the current times the voltage to give me the watt. Okay, the power output. And here, this is the voltmeter, and this is the screen for the voltmeter here. Okay, these here on this side, this is the solar constant. Assuming one of these cells, I'm controlling it. The other, I'm just giving it 1,000, and this 1,000 is watt per square meter. And this is the 0, and then I can control it. I assume, I don't know, say 50% shading, or 20%, or 10%, or 90%. I can control it from here, and it's very simple. You just double click on the block and change this figure here, this number. Okay, and here even these I can change them. Anyway, so this is basically the circuit. So it's very simple. I don't want you to get put off or overwhelmed by by all these blocks. Okay, yeah. And then what's nice thing about the Simscape, instead of having the individual cells, here I came and created a subsystem of 23 PV cells. So here there are 23 PV cells, and here 23 PV cells as well. So the total number, I'm assuming this is a panel, okay? This is a panel of all connected in series. And so the total is 46. And I left one of them here separately, is not part of this system, or it's not part of this system, is in the middle. And this is the one that I'm going to control the shading on it. Okay. The others, I'm just assuming, a constant, solar constant of 1000. Okay. And then these are, exactly the same devices. I have the ammeter, I have the voltmeter, and this is the load. And these are, the readings for the voltage and the power output and the current, so it's exactly as the circuit I explained earlier on. Okay. And here I have different cases. So previous one was 0, solar constant. This is the shaded cell, okay? These are not these systems. These are on full on 1000. I fixed them at 1000 watt per square meter. So I'm just controlling this one here. So this is at 100, okay? And then I come here, this is 200, the watt per square meter, and then this is the 300. And I don't know if you can here, if you can see these readings. The reading changes, as the percentage shading changes. Okay, so this is 400, the solar constant on the shaded cell, and so on. So I have, I think, about 10 different sets of readings. This is 900, this is 1000. So it's completely unshaded, this one here, this case. And then what I did, I came and I did, a script file and plotted the power output of this panel against the percentage shading. Okay. This is the curve. So you can see here, as the shading, this is a shaded cell. So one cell, and this is the output, this is the total output, okay? Output power of the total panel. So just one cell controlling the output power of the whole panel, okay? And as the shading, the percentage increases, the output panel of the output power of the panel drops dramatically and is sort of exponential. Okay, drops exponentially. And I can show you here. So at 50%, I don't know, sorry, at 50%, this is the 50% shading. Yeah, this is 50% shading of one cell only. Okay, 50% of one cell only. Look what happens to the output of the panel. The output of the panel gives me only 40 watt. Okay, whereas it was 160. So it dropped by is only quarter. Yeah, it's only quarter. So it gives me only quarter when this is 50%. So we can see, the effect of the shading on the performance of the panel. Now, the question is, what causes shading? If somebody is doing it, it could be, I don't know in India how you use them, but in Europe, usually what we do, we use them on top of the roof. So we have the pitch roof, the inverted V shape, and we put them on top of the roof facing south facing. And sometimes you have the chimney, the weather is cold there, and it's tradition, to have the chimney for the fireplace. So sometimes you have a chimney blocking the light or the radiation, the solar radiation on the panel. So this could be one of the reasons. It could be nesting, especially on the top of the roof. You is not easily reachable. Sometimes you have bird nesting, in a corner or on side of the panel, and the owner of the house, the people, they are not aware of that their panel actually is being paralyzed, is not working, is not producing any significant amount of energy, and they are not aware of it. Okay. This is why it's better to have it in a clear place, and we have to pay special attention on cleaning, physically cleaning the surfaces of these panels. Okay. I think I've finished, and I don't know if you have anything, to add, your comments. And thank you very much for, you've been a great audience.
Thank you,
Okay,
sir.
I'm back. Yeah, thanks. Thank you.
Thank you, sir. We'll go ahead and take some time for questions now. Just a reminder for the participants, please be sure to type your questions in the chat box so that we can ask it to our chief guest. And we have a question, sir. Sir, have you implemented and checked it in real time? What was the efficiency?
Yes, actually, in real life, we've done some partial shading on panels, and in one particular case, is funny, is not is anti-intuitive. You cover a cell, and that particular cell start warming up. Okay, so the one under shade, you shade it starts warming up because the diode is, as I said, is a diode. As in the reverse bias, apparently it was going beyond the breakdown. So it was consuming a lot of, or dissipating a lot of power, a lot of heat. But of course, this is not the case with all the panels. But we've done some tests, yeah.
They have asked what was the efficiency. Is that comparatively real time and the simulation in the MATLAB?
It is the same thing, with the Simscape. Sorry, really, you could program your panel. The cell. You could put real parameters from the data sheet of your panel. This is the good thing. This is why I like the Simscape. I use Simscape for other applications as well. This is not the only thing I use Simscape for. By the way, Simscape even for mechanical, for chemical engineering, for mechanical, you can have, say, spring mass damper. You could simulate it using Simscape. You can simulate electric vehicle, the batteries, using Simscape. So you could put real parameters in the Simscape, and it will behave exactly like real life panels. Yeah.
Thank you, sir. Thank you. Is there any technology like using sensors to rotate the solar panels only towards light and heat to avoid shading?
Well, you mean I don't know if the person who answers this question, if they mean the tracker, sun tracker. Yeah, I personally have done some sun tracking, you know, and they are 3D or 2D, so you can just keep it, you know, in one tilt angle, and it just rotate it, you know, to the say to the north and to the south, okay, or east and west, okay. But you can change the tilt angle as well, because we know the Earth, the planet Earth, is a little bit tilted. So depending on the season, the sun is on different angle to the Earth. So we could compensate that. And there are some equations as well. If somebody is using, say, I don't know, a microcontroller or some sort of controller, they can program it. You know, like Arduino. If you're using Arduino, you can program it. You can insert this equation in the Arduino and give the day, you know, which day of the year, and it will do the tracking for you, you know, in 3D. So it will according to the time of the day, it will expect, you know, where would be the maximum power. Yeah.
Okay, sir. One person have asked you to explain again 3 PV cell modeling.
3P,
3 PV cell
3
model.
PV, yeah. Yeah, this one here. Yeah, what I said here we have a solar. This is a solar cell, okay, and then there is another one here, and there is a third one here, okay. I've connected them like batteries, you know, as I said, is simple batteries. So just imagine you have batteries, okay, and you have another battery, and you have a third battery, okay. So you connect them in series, and you put a load, some sort of load here, okay. So it's simple as this, okay. So I put these two, I kept them at 1000 watt per square meter, and the other one, the third one here, I control the percentage shading on it, okay. So started with 0, you can start with 0, and then go gradually until you reach, you know, full power, you know. So this is what I did. The thing here, as I said, you know, don't get overwhelmed. Where's my pointer? Control. Where is it? This is the pointer. Okay. So here, this is an emitter. I've just this is the top part of the, say, battery or the cell, and this is the load. Okay, so it's very simple circuit really. This is the emitter. I've inserted the emitter inside the circuit, and then I'm monitoring the voltage across the load, the output. This is the voltmeter here. Okay, and then I'm taking these are just converters, you know, these blocks, and then I multiply the current and the voltage here, multiplication, to get the power. So this gives me the power output of this panel at this particular load value. Okay. The best thing, you know, this is where the MPPT comes on. So we could add here a switching device. We could add here somewhere a switching device to get, you know, the maximum power of this solar panel. And the switching, we do the switching, we change the average, okay, the average output of this to match the load. So when we have the load as a resistance here, I'm talking, the load with the internal resistance of this panel, they match, we get maximum power transfer. If we don't get this, really, we will be, the solar panel itself is already limited in terms of efficiency. And then we lose further because of the mismatch between the panel and the load. Any other question?
Yes, sir. Thank you. And one person have asked, what is the research scope in partial shading?
Sorry, say again.
Research scope in partial
Uh,
shading.
in partial shading, yeah, really, this is a problem being overlooked. Not many research, in this, and the manufacturers as well. This including Tata in India. I don't know. A few years ago, they were manufacturing it with in collaboration with the British Petroleum. They were manufacturing panels, and I've seen their panel. I personally haven't used them, but I've seen them because I was working in Dubai, as a company director for renewable energy, and we were buying panels from all over the world, from Japan, Kyocera, and from China, from Germany, and we bought some from Tata as well, from India. Yeah, this problem being overlooked, but the thing is, uh, because nowadays the design of the solar panels are really very rigid, so it doesn't cause damage. Not like before. Before, if you have a problem, as I said, in one case we were getting heat. You cover the cell and you get heat in that cell because of the power dissipation. So nowadays, the knee, and the reverse bias of the uh, of the cell is quite, distance. Okay, so this doesn't happen, but the diode the cell stays in the reverse bias, until the problem is solved. Okay, but people were overlooking it. This is a problem. The partial shading probably the most a problem. We had a problem with a client actually from Saudi Arabia, with the dust, in the sand in Saudi Arabia, and their panels, apparently it was covered with sand, and they were not aware of that they need to be cleaned. Okay, so they called us, and he was complaining, that we sold him a system that's not working. So, so I told him, are you cleaning? He said no. He said, what cleaning? Okay, I told him, you need to clean your panels regularly. Okay.
Okay, sir. Thank you. And one person have asked, is cooling of solar panel required when the sun temperature is more? And also explain the methods of cooling. If the sun's
Yeah,
temperature is more, is the cooling required or not?
yeah. Actually, I had a PhD student, working on the effect of temperature on the performance of solar panels. In this part of the world, I'm based in Iraq at the moment, as in Kurdistan, in Erbil, in the city of Erbil, at Tishk International University. This part of the world, and perhaps in India as well, the weather gets very hot. The performance of the panel. Let me just draw something here. So if we have, sorry, where is? Yeah, so if we have, this is the characteristic curve of the panel, okay? As the temperature, so this is the current, and this is the voltage. As the temperature increases, what happens? This it goes like this. Okay, sorry, where? Yeah, it goes like this. Okay, so the curve moves this way. Okay, I don't know why this has disappeared. Okay, so it moves this way. Okay, so the output power reduces Although there are two factors actually affecting the panel. You have the current. The current increases due to the increase of temperature. Okay, the current actually increases, but the voltage decreases, and the effect of the voltage surmounts the increase in the current. So the overall performance of the panel get reduced, okay, get degraded. And there is another thing as well in the hot climate. You know, the panel, usually the solar panel, they lose this or get degraded yearly by the efficiency decreases by something, you know, about 0.5% to 1%, between 0.5 to 1%, reduces yearly. Okay, so in obviously in hot weather, this is accelerated by the hot weather. Okay, although we have, you know, in this part of the world, we have the solar constant is quite high compared to other parts, especially in the northern hemisphere. You know, in the say in Europe or in Finland, in these, you know, Scandinavian countries. Here is much more. You know, the solar constant is much higher, but we have the heat as well with it, and the effect of the heat actually comes from the upper. You know, we have the visible light, so we have the infrared, and we have the ultraviolet light. You know, so it's the bandwidth of the visible light between these two things. You know, so we have from one side, from the lower side, frequency wise I'm talking, from the lower side is the infrared, from the upper side, the upper frequency is the ultraviolet, and the ultraviolet get converted to heat. Okay, and this is why it's good for disinfecting, you know, especially at this time, against, you know, the viruses and the microbes, you know. So the ultraviolet. So the ultraviolet during the summer is much higher and causes heat, you know, in the panels. I hope I answered your question.
Yes, sir, that was an informative answer. And one last question.
Yeah.
Which solar panel works best in shade?
Well, let me. Actually, I've used a one type manufactured in Japan, and it's called the manufacturer is called Kyocera. I found them, you know, they're quite robust, really. You know, in Kim, they are, you know, as we say, they are the Mercedes of the solar panels. You know, when it comes to the solar panels, they are among the best. But as I said earlier on, you know, the solar panel, really, they are just a converter. They convert photons to electrons. So if you put your panels in the shade, you will have less photons. Less photons, it means the generated electrons will be less as well. So I know you know, you need to sort of compromise between the two, the heat and. But I mentioned earlier on, you know, I had a PhD student. We used a solar chimney to cool down the panels. You know, solar chimney. You know, you have a pipe, and then you, due to the heat, you create a draft inside this pipe, and you force the air to go over or underneath the panels, and it will cool it down. Okay, and in this case, actually, with this particular students, we're even using water, you know, spray the top of the panel. Say this is the panel, so we're spraying on top of the panel, like water, you know, a douche, okay, to keep it cool, you know. But it's not is not realistic really. Okay, because with the evaporation you start having the salt builds up, and then you have other problems. But the best thing we found out that the solar chimney can work quite good. You create a draft, and you force the air to come in the vicinity of the panel, whether top of the underneath, and then rises up vertically. And we found this is quite useful. But let me be frank with you. I've worked in the industry. I'm academic, but I worked in the industry as well. Nobody bothers with cooling. Okay, the reason is the solar panels are so cheap now. So okay, you get degraded. The output, the efficiency, the overall efficiency or use system will get degraded by how much? By 10%. Okay, I add up panels, 10% more. Instead of having, say, 100 panels, I put 110 panels, okay, to compensate for the loss of power due to the heat. So this is the technique. I'm talking commercially. Commercially, people use this technique. Okay, they put extra power to be in the safe side. Okay, so nobody bothers with cooling. Because the good thing about the solar, there's no moving parts. Okay, so it's quiet. There is no moving part. Not like you have pistons or rotating things, and then you need the maintenance. These are the maintenance of solar panel, apart from the cleaning of the surface of them. Depends on which part of the world you are in. They are very very low on cost in terms of maintenance, and they are quiet, without noise, and you can erect them anywhere. You can put them even on top of a mountain, or on the side of a mountain, or on top of the roof, in areas that are not going to be used, for agriculture, say. So it's quite useful, and to compensate for the loss due to the heating, we just use more panels.
Thank you, sir. Thank you for the
Thank you.
suggestions.
Thank
It
you.
looks like we have covered all the questions. Sir, is
Okay.
there anything else you would like to share?
Well, I really been a great pleasure, for me to be among you guys here, and I'd like to thank you personally, and to Ms. Elizabeth as well, and Professor Praveen, and Mr. Ganesh, who put me in touch with you guys, and I hope this won't be. It is the first, but I hope it won't be the last. So we'll stay in touch, hopefully.
Sure, sir. Sure. Thank you. That was great. Thank you, sir,
Thank
for
you.
this wonderful and informative session. And thank you, Praveen, sir, for coordinating this webinar. We thank all the participants for joining us today. Hope you would have got a lot of information about partial shading of PV panels with MATLAB analysis. And thank you, sir.
Thank you.
We shall stop the screen sharing.
Okay.
Thank you very much.
Okay. Thanks. Okay. And I hope you stay quite well and safe. Okay. Okay. Bye bye.
Our upcoming
I think you've been
webinar.
recorded.
Sir?
Sorry. I think you've been recording. Yeah. Would it be possible to have a copy?
Yes, sir. Yes, sir. Sure.
Okay.
Sure. We'll
Thank
be
you.
sending you the
Thank
copy.
you.
Thank you, sir.
Yeah. Okay then. So I'll be leaving then. Thank you.
Thank you, sir. Thank you.
Okay.
Our
Take care.
upcoming webinar is on Kanavugal by Mr. B. Venkatesha Perumal, software designer, engineer chapter lead, ANZ Bank, Bangalore, scheduled on June 6th, that is tomorrow evening, 4 p.m. to 5 p.m. I request all faculties and students to attend the webinar and get benefited. Meet you all in the next session of our webinar series. I kindly request the participants to fill the feedback link with correct mail ID. I repeat, participants, please fill the feedback link with correct mail ID. Link for the feedback form will be posted in the chat box and in our YouTube live streaming page. Please fill and receive your e-certificates through mail. Participants kindly complete filling feedback form within 30 minutes after the session gets over. We like to inform that feedback link will not be shared through WhatsApp or mail. Feedback form will not be shared through WhatsApp or mail. Participants, please fill the feedback link with correct mail ID. Thank you all for your participation. Stay safe.